Today, we begin Unit 2, Inequalities. And as we start talking about inequalities, you're going to notice that there are some subtle differences, but also a lot of similarities to our previous unit, which was equations. Let's get started. First, let's define inequalities. An inequality, and this is where you'll fill in your notes with me. So, an inequality is a mathematical sentence that compares expressions. An inequality contains the symbol less than, greater than, the less than or equal to, or the greater than or equal to signs. And to write an inequality, you're going to look for the following verbal phrases when you're doing word problems that determine that it's time to use an inequality symbol. Okay, so here are some really common phrases in word problems that will lead you to know, oh, it's going to be one of these kinds of problems that's going to require an inequality. So first one, and probably most common for our greater than sign, is simply greater than. Okay. For the greater than, sometimes we also see is more than. Some quantity is more than another. Okay. Those are very common verbal cues that let you know that you're dealing with an inequality. That is a greater than symbol. Similarly, for the less than, they might just say this quantity is less than another. Or they might say something like is fewer than, which is just a synonym for less. Okay, and those are also really common word problem vocabulary words that will lead you to know, oh, this is not an equation, this is going to be an inequality. The less than or equal to sign has a few more. Okay, and in this one, we'll talk a little bit more about. First of all, it might just be as simple as is less than or equal to, right? Just the obvious here, or equal to. Another one might be is at most. And so I want to talk about this one for just a moment because at most might initially make you think, oh, greater than, because most. But actually, think about it. When we say this in English, we actually mean sort of the opposite. At most means that's actually a less than or equal to. So if I say, you know what, I'm going to eat at most 4 cookies, that really means that I'm trying to plan, or I'm planning on eating less than or equal to 4 cookies. That 4 is the max. So it actually, even though the word most is in there, it actually means less than. So that's a tricky one you want to keep in mind. And another one is no more than. Okay, same thing. I want to eat no more than 4 cookies. I want to eat most 4 cookies. Or less than or equal to, which is probably pretty obvious, right? All right, very similar here on the greater than or equal to, right? We might have a really obvious is greater than or equal to. But we also might have something that says is at least, right? So you got to be careful with this one again. The word least might kind of, trick you into thinking, oh, least, that's going to be a less than, but it's actually a greater than or equal to symbol. If I want to say, you know what, my goal for this year is to have a grade of at least an 85 in algebra class, that means that I want my grade to stay greater than or equal to 85. I don't want it to be any less. That's the lowest I want, right? So even though the word least is in there, it actually means a greater than or equal to sign. And then very similar to that is no less than. It's also a common one. Again, I want my grade to be no less than an 85 in algebra. That actually means you want it to be greater than or equal to an 85 in algebra. So those are common words to keep in mind as we're doing this and when we start kind of tackling some word problems. The other big difference for inequalities is that we graph our solution because unlike in our previous lesson, our solution is now going to be an infinite set of numbers. So when we finalize an answer, right, and we find out, oh, I want my grade to be at least an 85, that means that there's a lot of grades that could fit that category, right? I know most of our grades go to 100 in that case, but certainly any number between 85 and 100 would suffice. It's not one final answer that makes it correct. There's actually a whole set of numbers. So to illustrate that it is a whole set of numbers, we quite often graph our solution on a number line. So if in words we have found out that x is going to be less than 2, for example, well, first of all, let's go ahead and remember what that symbol is and practice our little symbols here on Cami. So if we have a less than, that's going to look like this guy right here. And then I'll just move that up a little bit if it lets me. Thank you very much. Okay. So if it's less than 2, it looks like this. But when we go to graph this, let's talk about how we graph this. We're going to look for this boundary number 2. And the first thing we're going to do is put a circle either on it or right above it, like that. And then if it's everything less than 2, then I want to essentially illustrate that on my number line. What side of my number line represents all the numbers that are less than 2? Oh, well, it's going to be, everything in this direction. So you either highlight or you make a nice, clean line and an arrow. The arrow is actually really important because it says, hey, even though I'm going to stop drawing here because I don't want to draw forever and for the rest of my life, I want to acknowledge that everything continuing in that direction makes sense. So anything less than 2 is any number that is on this side of the number line going on forever toward the left. And I make a circle at the 2 to denote that that's sort of the limit or the end point of that, but I'm going to leave it empty or open so that I recognize that 2 is not part of my anxious. Actually, anything less than 2, not less than or equal to. So since 2 is not part of the solution, I'm going to leave it as an empty circle so that okay, this is my stopping point, but 2 doesn't actually is not included, right, in our solution. Okay, how about the next one? X is greater than 2. So again, we'll use our greater than symbol over here. Looks like this. If I can insert that. Come on, Cami. All right, so greater than, there it is. And then I will move that over a little bit. And then let's graph that. So everything greater than 2 would still have our boundary number here at 2, but it would shade the other direction, right? So here's our boundary number. I don't put an open circle on that, and I want everything greater than. Well, everything greater than is always going to be on the right side of our number line. So any number toward the right here that fits this description would work here. And then you would put your arrow to show, hey, it keeps going and going. So if I wanted to use a number 2,392, that would work. Right? All right. And then, of course, less than or equal to includes the equal. So that means it includes the 2 in this particular example. So if I want all the x values that are less than or equal to, then I'm going to use this symbol. And then as I use that, the difference here from the first one and the less than or equal to is that when I mark my boundary number, I got to go to the drawing symbol here. When I mark my boundary number, I'm actually going to fill it in. And then I'm going to say everything that is 2 or less than 2. And so notice that's a big difference here is filling in that circle. So by that, I'm saying it's anything less than and including the 2. And as you can probably guess here on the last one here, the greater than or equal to, of course, we'll use our greater than or equal to symbol. Looks like that. And then when we graph it, in this particular example, our boundary is still 2. We're going to keep that consistent so you can see the difference in the graphing, but it's greater than or equal to. So once again, since 2 is part of our solution, we'll fill it in. I'm kind of going out there. And then or everything that is 2 or greater than. So you can see the difference here in our graphing. Okay, so to kind of summarize, these are the main differences that you're going to see when we're working with inequalities compared to what we did in the last lesson. Okay, so the final thing here is let's talk about the solution, right? So obviously these guys have more than one solution. Oftentimes they have many, but just in a specific direction. And so the graph, like what we did right now, the graph of the inequality will officially solution set of the inequality on a number line. And then we have a special symbol when something is not equal to, right? On our graph, we agree that that means that we're actually going to leave that as an open circle, right? So an open circle. And then a circle that has been filled in on the graph, that actually means that the number used is a solution to the inequality. Okay. And then last but not least, we make sure that we include an arrow, right? To the left or to the right will show that the solution continues infinitely in that direction. All right, so those are the kind of key factors here. There's going to be a few more differences about inequalities, but these are really at the heart of what what's additional, what's added on that we didn't have to deal with when we did equations, right? So let's start solving some of these. Before I forget, let's talk a little bit about sets. So I'm going to go over this very quickly. We're not going to spend a whole lot of time, but it's kind of cool to just be exposed to it. This is something that you're going to really dive much deeper into in Algebra 2 and in Pre-Cal. But sometimes, so I talked a lot about the graph, and the graph is going to be our primary method for showing our solutions. But there are a couple of other options here, and that is called set builder notation and interval notation are both options. Okay, they give us a shorthand option for describing a large set of numbers, or any set of numbers, honestly. So with inequalities having more than one solution, these guys can come in handy. Okay, so they're frequently used in higher mathematics, like I said. Set builder is a quick way to state all the numbers and properties of a specific set. So a set is a fancy word for a group of numbers, while interval notation is a representation of an interval as a set. Okay, so again, I'm going to kind of just give you a quick little intro to this, but this is not a huge aspect of Algebra 1, so we won't spend a whole lot of time on it. But the main things is in set builder, you kind of still see the inequality in there. They're just really defining what numbers within that inequality work. So symbols like the double bar R, are often used when your numbers, when your answers are all real numbers. But there's other symbols as well if it was only whole numbers or maybe only integers, things like that. Okay, and then this little symbol here stands for an element of, so a part of that group. And then the bar is sort of about to separate the set from the limiting factors, which are your inequality. Okay, and then that's set builder. So if I was going to write this in set builder and I say my solution is everything less than or equal to -2, okay, then in that case, I would probably just say, okay, so basically my solution set, and so I would open one of these little squiggly brackets, and I would say, in this particular case, I might say something like, so X is going to be in all real numbers. It could be a fraction, it could be a decimal. It doesn't look like there's any type of limiting factor to that. So the X in all the real numbers such that X is less than or equal to that -2. And then I would close my set. So I would just it's basically, I always say this is kind of like speaking, our normal English today versus like Shakespearean English. It's just a little bit more formal and a little bit more informative than where we're saying X is the set of all real numbers such that those numbers are less than or equal to -2. So this is just defining that it could be decimals, it could be fractions, it could be any kind of real number. We're not limiting to maybe whole numbers, that sort of thing. Okay, now let's talk about interval notation. If I did this in interval notation, it would look almost like an ordered pair. It looks often like these two examples down here. And in this case, we would use a parentheses if the limiting number is not included. So kind of like the open circle that we did up here. If this was an open circle, I would know I would have to use a parentheses. That means not included. And then a bracket, more squared off bracket, if it were a closed circle or a filled in circle on the graph. Okay. And then of course, if the numbers go off to infinity, like with our arrows up here, right, it goes on to infinity, then we use our infinity symbol, but we never include, right? Infinity, you can never actually reach it. So you get a parenthesis. So let's see what that would look like in interval notation. In interval notation, this is telling me X is everything less than or equal to -2. That means that it starts at -infinity. It could go on forever on the left, and it goes from -infinity on the left all the way up to -2. So it's all the numbers between -infinity and -2 are what's valid here. And then I would say, oh, okay, but -infinity is never included, so that's going to be a parentheses. However, this would have been a closed circle. It's got the or equal to on there, right? So we're going to make this a sharp bracket like that. So these, all three, say the same thing. Okay, these are just different notations for writing that infinite set of numbers with set builder or with interval. Okay, so feel free to kind of practice some of those. I'm going to move on to the second part, which is actually starting to solve. Now, this is where it starts to feel very familiar, or at least I hope it does, because you're going to notice that many times, a lot of the steps for solving inequalities are going to be just like what we talked about in equations, right? So let's start off by just in words. When we're adding, let's talk about the addition property of equality, which we've already played with a little bit here. But when we do the addition property of equality, adding the same number on each side of an inequality is going to still produce an equivalent inequality. So we've talked about this before with equations. We're just reiterating it here. So let's say that I started off with a -3 is less than 1, which we know is a true statement. If we decide, for example, to add a 5 here, as long as we add the 5 on the other side as well, our results are still going to be equivalent. So, or it's going to still be a true statement. So I would still get something that says 2 is less than, all right? So 2 is still less than, if I could click that and make it nicer. No, you don't want to move for me? There it is, okay. And then on the other side, I would have a 6, right? And so when I put my 6 in here and I try or I test my inequality again, I notice, yeah, you know what? You're absolutely right. This is still true. 2 is still less than 6, right? So it still works. And so that property of equality still holds true as a property of inequalities as well. So if A is greater than B, for example, and you add some quantity on both sides, then it is absolutely true that A plus that quantity is still going to be less than, in this case, oh no, this one was greater than, so greater than the B plus that same quantity, right? So if we start off with a statement that is true where A is greater than B, then A plus some quantity is still going to be greater than B plus that same quantity. So that allows us to add the same on both sides of the equal sign. And guess what? Same thing is true for subtraction, right? So let's talk about subtraction down here. So subtraction or subtracting the same number from each side of an inequality will still produce an equivalent inequality. So it is still true there. So let's do this example. Let's say I start off with -3 is less than or equal to 1, which is true. If I subtract 5 on both sides, or I should say apply a -5 on both sides, then we get a statement here where, let's see, -3 and -5 is now -8. And that is, according to them, hopefully, right, still going to be equal to, or less than or equal to, sorry, the other side, which is a -4. Okay. And so if we do that, so -4, there it is, right? So we know that that's a true statement there. It would still be less than or equal to -4. So that makes sense. So the subtraction property of equality is still true when we have inequalities. There's still a subtraction property of inequalities here. So any value that we started off with, A is less than B, then as long as I do A minus the quantity, and then that's still going to be less than B minus that exact same quantity. That's our big idea here. Okay, so that allows us to use the same sort of steps and inverse operations on both sides to isolate the variable as you did before. That's the main idea here. So let's practice a couple of examples, and then really the added step that we're going to be dealing with is graphing our solution at the end. Okay, so if I start off here with this particular problem, x minus 3 is less than -4. I know that I want to get x alone. I look at what they did to x. They were doing a negative. They applied a -3 or subtracted 3. So the opposite of that is a positive 3. And if, of course, if I do that on one side, I've got to do it on the other side. It'll cancel my 3's here. I'll get a solution that says x is anything less than or equal to, and then let's see, what's -4 and a positive 3? Those signs are different, so I'll find the difference. It's a -1. Okay, so my solution is any x value that is -1. So I just want to really, I guess, emphasize here, right, that there are infinitely many solutions that will make this true. As long as I plug in a number here less than -1, it will make this inequality true. So that is an an infinite list of numbers that would work there. I could use -2, -10, -1,000,000, -432, negative anything we want, -1.5. Would all make that true, right? So since there's a very large list, and in addition to actually finding the solution, we graph our solution quite often, right? So I will look at my boundary number. Okay, it's a -1. I want to make sure I have enough room for a -1 here. So maybe I'll put a 0 over here and then make this my -1. And now, you don't have to label every tab, as long as you have a few labeled to kind of establish where 0 is and what you're counting by, and making sure you know that negatives are going to the left, or that things are decreasing, I should say, to the left and increasing to the right, then we can graph our inequality. So our boundary is -1, so I'm going to put a big old open circle right there. And it's everything less than, so it's going to be everything less than is to the left on the number line. And that would be my graph that visually represents this list or this set of numbers. Okay. And so again, boundary number was -1, but I left it open because there was no or equal to, and then to the left because it's everything less than. And in fact, I'll give you a big hint. One of the big reasons I was talking about in the last unit, putting your X variable on the left, not only is it going to make a big difference in reading these, but the inequality almost kind of gives you a big hint or reveals which way your arrow should go, which is kind of cool. But that only works if your variable's on the left. So let's talk about number 2. Let's try this one. I want to get H alone. This time it's all around the other side. So I want to get H alone. What did they do to it? They added a -3. So I think about what's the opposite of a -3. It's a +3. So I'm going to apply a +3. Of course, if I do that on one side, I have to do it on the other side. This cancels. That leaves my H here by itself. My symbol is a greater than symbol. And on this side, -3 and +3 also cancel and leave me with 0. Okay, now this can be hard to read. This is kind of what I was hinting at in our previous unit. So I'm going to rotate this entire statement so that it's easier to interpret and understand. So if 0 is greater than H, then that means H is less than 0. So notice that the symbol's still pointing, like my little Pac-Man or alligator mouth is still opening toward the H. Towards a 0, and the little pointer is going towards H. That's still the case here. My Pac-Man mouth is still opening toward the 0, and the arrow is pointing toward the H. So it's the same statement, just rotated, but this is so much easier to read. So I'm going to ask that you always put your variable on the left when it comes to these inequalities. Not only that, but it's going to be a lot easier to understand now how we graph this. All the H's that are less than 0 is a lot easier to think about and graph than 0 being greater than H. All right, so let's put our 0 nice and centered. I'll do a 1, a 2, a 3, just to kind of establish what we're counting by here on our number line. That's plenty there. And then it's going to be an open circle again because 0 is our boundary, but it is not included, right? So I'm going to put my open circle there, and I want all the H's that are less than. That makes it really easy to know which way to put our arrow now. Okay. All right, and then just like our previous lesson, sometimes you have to do a little bit of simplifying. Sometimes you have to combine some like terms before you start to solve. And so we'll do a couple of more here. Let's combine these guys together. And before we begin, right, I always emphasize that before we begin, simplify each side. So this can be simplified here. So I'm going to hold off on starting to eliminate anything. And before I do that, I'm going to go ahead and simplify. 4C minus 3C, that's just 1C. Okay, so I can simplify that together and make it nicer to look at. So I've got that now. And now I get that C by itself by getting rid of the 10. So we'll do the opposite here, a little subtraction property of inequality, which we know will still work. We'll do that on both sides. It cancels on this side. And on the left, I've got 12 minus 10, which is 2. So I get left with a statement that says 2 is less than or equal to C. And again, I do not want the C on that side, so I'm going to rotate my entire statement so that it's easier to interpret and read. So it looks like that. C is greater than or equal to 2. That's a lot easier to think about wrap my brain around and graph. All right, let's go ahead and graph this. So on our graph, I'm gonna put my 0 over here, 1, 2, 3, 4, and so forth. Maybe a little -1 over here to make sure we all know where we are. And then my boundary number is 2, but this time, guys, notice this is all the c's that are greater than or equal to. So I need to make sure I fill this in. And then greater than is to the right. All the numbers that are greater than will be increasing toward the right. So there's our graph. So try number 4 on your own, and then we'll talk about that one in class. Let's go on to just finish this up. We're going to do 5 and 6, and then we're going to leave these word problems for class together, for our time together when we're live. Okay, so let's talk about the difference of a number and 9 is fewer than 4. So first, this is a word problem. So first we have to write the inequality that represents this, and then we'll solve it. Okay. It doesn't say to graph, so we'll save ourselves a little bit of time and not worry about graphing it. Okay, so let's kind of translate things. The difference of, so immediately I know, okay, difference really means subtraction. So I know I'm going to be subtracting here. A number, well, I don't know what that is, so I'll call that n, n9, so that's already a number, is fewer than, so let's think about what that symbol means. That means an inequality, right? So let's start writing this in. So the difference of a number and 9, let's go ahead and write that. That means that a number minus 9, so difference means subtraction, and number and 9, is fewer than, that means less than, okay, and then 4 on the other side. So this is a symbolic, mathematically symbolic way of writing the same thing that they had up there in English. So that was step number 1, is to write the inequality that represents the situation. And then it said solve that inequality. So now we'll take this n minus 9 and we will solve that. Okay, so if I want to get n alone, I'm going to do the inverse of that minus 9. So that means I'm going to add 9 here. That cancels. So I get all the n's must be, I'm going to write this over here. All the n's must be less than or equal to 4 plus 9, which is 13. Okay, and then you could plug that in and see if it works, of course. That always is a good option. Let me erase this from over here. Okay, all the n's that are less than 13. Let's try the next one. The next one says 6 is less than or equal to, so we've got a 6. Less than or equal to means this symbol right here. And so it's less than or equal to the sum of a number and 15. So sum means addition, and some number, which we don't know, so we'll call n, the sum of some number and 15. So there is our equation right there, or inequality, I should say. So that's the first thing they asked us to do, was to write an inequality that represented the sentence. Okay, and so now, maybe I'll make a little border here so that the work doesn't get all. Now let's solve that, right? So if I have 6 is less than or equal to n plus 15, then to solve that, I'm going to undo this. That's with my variable. So the opposite of adding 15 is subtracting 15, like that. Of course, if I do it on one side of the inequality, I have to do it on the other. This cancels. So 6 and a negative 15, those signs are different. So I'm going to find the difference. That's going to be a negative 9. And that's still less than or equal to our n. We talked about not leaving n on the right. So then I will just rotate this entire statement so that it looks like this. And that would be the solution to the inequality, any number that fits this description right here. All right, we're going to leave the word problems for our time together. So this completes your lesson and notes.